Okay, so yeah, what I'm going to be talking about here is our Navops product suite, specifically Navops Command, which is our new way of adding rich policy and rich policy that we've developed over time at our company for the HPC workspace to, or the HPC space to Kubernetes. So first I'm going to go through a quick introduction of me, our company. I'm going to kind of talk about the way we look at scheduling and workload management. And then I'm going to go into a description of Navops Command and give you guys a quick demo of what we're currently doing right there. So I'm the Director of Engineering and the Chief Architect here at Univa on the Navops product suite. I've been at Univa for 10 years. We've done quite a few things over those years, and I've been involved in a lot of these different products. So Universal Resource Broker, if you guys are used to or run Mesos before, it allows you to run Mesos frameworks directly on our stock scheduler. I've also done a lot of work with cluster provisioning. That was the core product I started working on when I came in for doing Linux and Solaris cluster provisioning. And then also a lot of work on Grid Engine, which is really going to be the core of the scheduler inside of the product that we're going to be talking about tonight. And then quick, who is Univa? So we're a leading innovator of software in the HPC space. So you can see down here, these are the types of people that we work with, the types of industries. And they typically are running very large scale computer simulations. So for like the oil and gas, like Saudi Aramco they're doing seismic simulations to determine the next place to drill a well. We have life sciences, which are either doing drug simulations or doing genomics analysis, things like that. So a very large set of customers. And they're all really throughout the world. So through this kind of customer set, we've really had a view on very large clusters for a very long time, people running lots of different types of workloads, very complex organizations. So we believe that through that, we've learned quite a bit. So this is kind of some of our general statements in what we believe when it comes to scheduling and workload management. So generally, we live in a world where resources are finite. So you can look at that real simply as being your physical on-site servers. You obviously can run out, but also you can look at it as a software control thing, like quotas in your groups. Once a user or a group hits their quota, they're now not able to run potentially all of the work that they want to run. And then you also have budgets. This really applies when running in the cloud. You may be only limited to such a burn, and when you hit that, you need to decide potentially what needs to run and what shouldn't run. We also really want to make sure we get the most done with what resources we have and the money that we spend on resources. So this is things like, we want to make sure we always meet our application SLAs. We want to be able to, while doing that, provide nice agile development environments for our development teams sharing those resources. And we want to be able to analyze the results of the decisions that we've made when placing our work so that we can really do things better. So our solution in general is combining clusters together to make larger clusters, reducing silos, and having all of your resources managed under one kind of policy. Our customers, may have 70, 100,000, core clusters, and they run a tremendous amount of different types of work through, perhaps 1,000 or so engineers. So we then will place, in order to manage all of that, you need to have a very rich scheduler to kind of handle all the business policy and the quota and make sure that what really needs to get run runs on the right resources at the right time. So these policies should be modified over time to make sure that you meet your business needs. It can be configured as the market and the needs change. So we really believe in order to meet these goals, prioritization is very important. And it comes in multiple ways. So first, you always want to make sure that your most important jobs have access to the most important resources. They should have first access. So something that's important wants a GPU. It should get the machine with the GPU, then a machine that doesn't. You also, when you have, when you are hitting limits, you want to make sure that it's the lower priority jobs that you preempt and skip or throttle, as opposed to your higher priority jobs. We also believe in general that the scheduler should have as much information as possible. This should be information about resources that are available on hosts, who's using the cluster, what work wants to run in the cluster. All of these things can help the scheduler make a better decision on what's the most important work and where it should be run. Things like, if this timetable as well is a major impact on should this be scheduled now or scheduled later. And then at the end, like I brought up earlier, you want to be able to analyze the decisions that the scheduler makes over time to make sure that you're getting the policy that you want, and it allows you to identify the resources in places where you should spend money. Should you start buying a certain instance type in AWS as opposed to another one? So it may be that you need more big RAM ones as opposed to more big CPU ones. So it's all of this is really kind of leading us to our Navops command product and what we're doing with that. And so what we're doing is we're taking what we've done with our HPC customers and we're bringing it in here to the Kubernetes ecosystem. So what that means is you'll be able to take your kind of random set of resources that are currently scheduled pretty much just based on what they request to now moving to our place where we can, with Navops Command, being able to schedule resources very effectively, getting good packing, getting the appropriate utilization and business policy enforced on the placement of your workloads. So, a little bit about Navops Command. This being the Kubernetes group, I know you guys understand the Kubernetes schedule very well, so we'll just start with that. It replaces the Kubernetes scheduler inside of Kubernetes. The Kubernetes scheduler is really all its interaction with the system is assigning a node name on a pod. It's a great clean interface, so it made it easy for us to develop Navops Command here, which actually runs as a pod on top of Kubernetes. It consists of 3 containers, and one that's really responsible for bridging the object model between our scheduler and Kubernetes, one that is responsible for making the actual scheduling decisions, and then also one responsible for providing a web user interface for the product. End users interact with our system using the Kube API server as always. So for an end user, there's nothing different. You don't have to learn our syntax. You use Kube Control. We do just simply add new labels and annotations that allow you to leverage additional policy inside of Navops Command. And then we also, the big benefit here is it leverages our core and proven policy engine. So here's the diagram of that architecture that I just kind of described with the containers. And you can see here that the end user primarily is working with Kube Control and the stock Kubernetes API server, whereas the admin's going to work with our web UI, as well as the Navops Control command line utility. So this is a utility that we wrote that's very similar to Kube Control in terms of interacting with objects in our bridge container, which is hosting an API server. This part over here is the policy engine, which is responsible for doing the binding of the pods to the nodes. So for the demo that I'm going to show here, we're going to kind of simulate this type of situation where you have a company that produces a web application as their product. And they have a Kubernetes cluster that's running Navops Command. And they're using that, a single cluster for all of their workloads. So you have 2 teams in this company, the production/operations team, as well as the core development team. The development team has 2 sub-teams, the guys who are working on the back-end part of the application, and the other people who are working on the front-end part of the application. The types of work that's being run, of course, the production team is running the actual production application out in the wild, as well as various production admin jobs. So these would be roll-ups of metrics or other types of analysis work that they want to run in the production environment. Whereas the development team they're primarily running CI tasks, so doing things like GitLab CI server or something, perhaps even like OpenShift. In my demo here, I'm going to be running on a single cluster, a single node cluster using Minikube. So before I jump into the demo, I know I went maybe a little too fast through any of that. Are there any questions on what we're talking about here and kind of what the product's all about? Yes?
So will you schedule across AZs and across regions?
Yes, we totally could. So right now, it's something that we're looking at evolving is kind of how we embrace the Kubernetes work that's being done inside of the Kubernetes community. But right now, we generally look at it as having a multi-AZ cluster and a multi even
you could do a local prem or multi-cloud provider cluster even under one kind of Kubernetes install. There are some other things that you have to consider with that, but that's our current approach to the federated, or the lack thereof of federated kind of Kubernetes clusters. Okay, cool. So we're going to start here. I'm going to show you the web UI. So this is the web UI inside of a Navops command. And actually, before I can show that, I'm going to show you the pods that are running. So here you can see we have our Navops command pod that's up and running, as well as our UI pod. Our UI pod just talks to the Navops command pod using our well-published API or well-defined API in order to get information about the system. So I'm going to log into this. So let me actually jump ahead. I'm going to show you guys the home page first. So here's the landing page for our UI. And on the left, we have the types of policies that we support in Navops command. So there are several listed in there, like pod placement, which allows you to decide if you want to do packing of pods, or you want to do spread of pods, or if you want to mix for some types of workloads and spread for others. The access control and runtime quotas is really our way of interacting directly with namespaces in Kubernetes. And portional shares is a way of dividing up your clusters into dedicating a certain ratio of your cluster to a certain set of identities inside of the organization. Over here on the right, we have some of the types of objects that can be configured inside of Navops command for attaching policy. So projects, first, they're pretty much an entity that kind of defines a class of work that a group might be doing. In our demo here, we're going to have like a project for the front end, a project for the back end, and a project for production. For user groups, you can group up users and really think of users more like owners of pods. So who's responsible for it? Who, when that pod has an issue, is the one getting the phone call? We also support application profiles, which are pretty much a definition of a container environment in which an application should run. So you can add additional things like additional resources, or add requests that would be preferred, resources that would be preferred, but not necessarily required. So here, I'll jump into the proportional shares page here. And this is, some people call this fair share, but what this really does, as I said, it allows you to break your cluster and divide it up into ratios of the cluster, or proportion of the cluster that will be guaranteed to different groups over some period of time. And this is a hierarchical configuration. Well, it's configurable in a hierarchical manner. So I'm going to load some data into that. And in order to do that, I'm going to use my Navops control utility here, because it's a lot faster than clicking through all of the individual dialogues. So I have a script that's going to create all of my resources here. So you see there immediately the configuration popped up in Navops command. Our API server supports a streaming endpoint. Changes are made available immediately. You can see the other types of things that I created in here I created 2 users, as well as some user groups. I created a whole bunch of projects, and also some application profiles. So I'm going to go through a couple of those here real quick. So you can see here in the project list, we have our back-end and front-end project to model the CI work, the back-end and the front-end teams. We have a production project that is going to be used by our production. Yes?
Can you zoom in?
Oh, sure.
Same with shell.
Yeah. Hopefully the layout looks okay in our web UI. Does that look a little bit better? Or does it need to be bigger? Okay. Then you can also see in here the user groups that we have. If you click on these, you can see the members of the different groups that are all already configured. And then application profiles, we have one set up for our AP front end that has some base memory requirements, and so one for our AP backend. So at this point, I'm going to go and actually submit some work to the cluster. So those have been submitted. So these are, just like, as I said earlier, they're going to be your standard looking kind of YAML files used by Kubernetes, except we're going to have a couple of additional annotations in here. So like this right here is the annotation, or actually the label, selecting the application profile that should be used when starting this replication controller. And you can see down here we're using the standard Kubernetes way of selecting a third-party scheduler. Right now we're still running the stock Kubernetes scheduler in the default mode, and then it starts up Navops command, but then any pod that has this annotation on it will be started by the actual the Navops command scheduler. So if I do a watch now, we'll see we have a whole bunch of work running. I submitted both backend and front-end jobs. So you see really all the backend ones kind of filled up the cluster before the front-end ones. And that's because of the way that Kubernetes works in creating resources. We created our backend resource, our replication controller first. It went and created all of its replicas, and then those all immediately got scheduled before the front-end jobs could get in. But now what you're seeing is that there is a leveling off between the front-end and the back-end jobs. We should see some more back-ends coming here. And that's because we have the proportional share policy configured here in Navops command. If you see right here, we've got a 50-50 balance between the back-end and the front-end. So this is something that's not available in normal Kubernetes. Normally in Kubernetes, whatever can get through the admission controller is what gets the start. So if you have quotas in the system, it will prevent the system from getting overloaded. But it's then who's ever just slamming on the API server, whoever gets in next, that's the one that happens to run next. So we, however, support a runtime quota in Navops command. That's what's really going on here. You might have noticed, well, actually, I showed you the prod one. We've got the CI backend and front-end YAMLs that I ran. You see they had a parallelism of 10. Both the backend and the front end had a parallelism of 10. Right there. But as you can see from that watch command, right, there's not 20 running. And that's because we have enabled in our system a quota on the running of these CI jobs. And really, you can look at it as we don't want the CI jobs to like overload our whole Kubernetes cluster, but we still want to have sharing between our backend and our front end jobs. What that's done is that's done through here in our access restrictions and runtime quotas. So if you go in here and you look at the CI quotas, you can see we've got a quota in here that limits the project's backend and front end, and then combined, it applies this limit to both of them combined to 10 pods. So what that means is it's limiting the aggregate of the backend and the front end to 10 instances. So that would probably lead you guys to realize that if you did one of these, you'll see that there are all 20 of them available here from the API server. It's just 10 of them are being kept in the pending state because they would be violating the quota if they were started. So if I go in here now to the proportional share section, again, and we go and we can go and we can just grab one of these and say like, I want to move to like an 80% front end configuration. You can just go in like this, and if we go back here, we can watch and we'll see that will take effect over time as these pods are created and destroyed. So those CI jobs, I didn't explain it really earlier, but they're just simple sleep jobs that are sleeping 60 to 90 seconds randomly so that we can get some turnover here. So are there any questions with what I've been showing at this point? Yeah?
When you configure the app profile, and when you set memory and CPU, is that right?
Yes, we had some memory and CPU in the application profile.
How do your customers typically determine that?
Yes, so this is actually a very challenging exercise. It's something that in the HPC space, it usually takes a while and it takes some real discipline. But typically, it's a lot of attempts really at running their applications. And they usually start big, and then they start pulling down to try to improve their utilization. So you can go and you can run your jobs. You can request your 100 gigs of RAM. You can run it, and then you can look at the usage when you're done and say, well, okay, that one I use 60. And you can look at that over a month and say, okay, really, 90% of the ones that we run that look like this are in 60, so we'll start moving down to 60 so we can get a better packing. Because yeah, hitting the OOM on jobs is really bad, especially for ones that run, for any significant period of time. So as you can see here, we've definitely settled on about the 20 to 80% kind of breakdown here between these, and we're keeping our controllers here up and running through the whole time. So at this point, I can talk through some more more types of use cases that we can handle here in the cluster. We can support things like interleaving here. And this is a really kind of cool bit of functionality that allows you to reprioritize your work such that you will always have kind of a certain ratio of one type of container to another type of container. And where we find this to be very useful, like let's say you have a multi-container application or a multi-pod application inside of Kubernetes that has a front end and a database. And then for whatever reason, there's a disaster and you lose a chunk of your cluster and you have to respin up that type of work and you might hit a limit. Well, there's nothing in Kubernetes that will make sure that the ratio of your front end to back end is maintained if there isn't enough to run all of the replicas that you specified. If you had 50 of both and now you can only run 50 instances, and you could end up in a situation where you have 40 of one and 10 of another as opposed to a 25 split. This type of system would allow you to make sure that when they came back up, they came up in the appropriate ratio in order to properly support your application. We also do the same type of thing for labels. So we don't support anything other than, as a consumable yet, CPU and memory for labels, for consumable labels. But you can add just standard labels like in Kubernetes and do like node selector on standard labels and then apply certain priority to those labels. So you could make a label called like high priority, you attach that to a job, you could then interleave on that one, like high priority and high priority 1 and high priority 2, so those kind of have equal priority, and then have some other medium priority that's next, followed by nothing. So that would just be then something you would select with a normal string on your pods. We also support, just in a more simple way, just standard like resource ranking, where you can type in one of the like CPU. We automatically detect the ones that are available there in the system, and you can then say people who are requesting like more memory get higher priority jobs, and that's generally a good thing. You want to always schedule the jobs that are requesting larger memory to prevent fragmentation of your memory space. So if all things are being equal, it's usually better to schedule your big jobs first. And then to go a little bit more detail about application profile, we'll go into application profiles a little more. You can also do this with the rankings of application profiles, where you can say certain ones are more important than others. And then the one last thing that I'll cover, I guess, before we wrap up for just full-on Q&A is all of the bits here inside of application profiles. So this allows you to delegate responsibility for application profiles. You can, throughout the identities in the system, you can say certain people have access or certain people don't have access. You can do here, like put on these mandatory resource labels. And these are done outside of the context of Kubernetes. So this isn't mutating your Kubernetes pod. It's just adding that as an additional thing that gets attached to the pod and scheduling it in, to the actual node. And for us, our information regarding the memory and the CPU available on every node, that's made through the, what's available on the Kubernetes API server. So we know all of the nodes, and we know how much memory and CPU that they have. So this would be, adding these types of labels would allow you to, just like, say, more like node selector. This one, desired labels, would be ones that you prefer to have, but aren't required. And we also have in here the ability to default assign a project. And that's why
production jobs in the previous list were running in the under production project. So that pretty much wraps this up. Are there any questions? Yes?
Is there any kind of auditing? Like, why did the pod get scheduled? It'd be nice to know later.
Yes. So there is, our systems records a complete accounting log. So all the pods that were scheduled at the time, how long they ran, how much time they consumed. Right now, since we're not hooked into the actual Heapster or C-Advisor, we don't have the actual memory and CPU consumption. We could do very easily the reserved resource consumption. So that would be like, you asked for 50 megs of RAM, you ran for an hour, so that's like 50 meg hours of RAM you consumed. We could do something like that. That's often how our users generally think of resource usage. It's not what you actually consumed, it's what you prevented other people from using. That's what they go for. So yeah, I mean, that's definitely something that we're going to be adding in with the addition to the Navops suite. We're going to be adding the control program, which is really going to look at the output of this system. It'll allow you to really make these kind of higher level decisions on what happened over time with the scheduling decisions of the clusters.
So, is that some kind of simulator so that if you have a new policy, it can maybe tell you what might happen?
So what I would say, and this is something that's really excited me when doing this project, because with Grid Engine, normally we're managing like actual physical machines. Well, in this product, we've pretty much taken Grid Engine and had it simulate a cluster inside of a single container. So we're not actually dispatching work on machines. So with all the work we did there, we now can simulate. So I've been thinking exactly how would we want to go and do that? I mean, we could what we would be able to do, for example, is like take an accounting file and run it back through, simulating that work.
Right.
There might be some things that we're going to have to do to tweak, like to speed up time, so that it doesn't take actual real time to do the simulation. But otherwise, yeah, we don't have it now, but I think what's cool, it's a total aside of an answer, but what's cool about the work we did here is it really opened the door for us to do that for both the Kubernetes space and even for now our general purpose clusters. So we're very excited about it. All right.
Cool. Thanks.
Yeah, no problem.
Well,
Yeah.
just keep going on that subject. Because this tool can manage the instance on different hardwares. So to measure the resource usage, CPU clock, memory type, you have to find a way to measure them in a unique format, like AWS. Otherwise, it's difficult to say which one's faster or which resource better.
So your question is, it's hard to tell.
Oh no, because I think your tool should on each node how many used CPU in a unique way to measure them.
Mm-hmm.
That gives the user a better comparison, a better reporting.
Right.
Because this one is not like AWS is already measured up for you. This one can go to any hardware.
Mm-hmm.
And virtual machine running on the different
Right.
hardware.
Yeah. Right.
Right?
Exactly.
You see what I'm saying? Yeah.
Yeah. So this is a big thing with our roadmap in Navops Command is, right now we're relying 100% on what Kubernetes makes available to us in regards to resource usage and consumption. And so since that's not built into the API server right now, what's really being consumed, we don't have the real numbers. But in a real Grid Engine cluster, we do have that, and that's really something that we want to add to Command.
Enterprise.
Yes.
I can imagine an old company, they have the IBM machine. They can put the Docker Nova. They can put it on the Linux server. How you compare the two resource?
Right. So, yeah, it's a challenge. It's a challenging thing, in the different places. I know fundamentally we are tracking all this, and we track it as easy to consume data, right? We have once the data is accurate, our numbers are in our accounting file. They're just more like CSV files. So you'd be able to pull out the numbers and be able to compare. So we would have it, but it's it would be our format. So, yes.
You mentioned the application SLA in one of your slides, if I remember correctly.
Yes.
So what is your product doing in terms of application SLA?
So what we're getting there is, like, let's say your application was required a certain type of latency or things like that, and you had
a horizontal pod autoscaler to kind of help meet that. So if that was something that was super important to you, those would be high priority jobs, super high priority jobs that might have dedicated resources up to a certain level. So that's the type of policy we can configure.
So let's say you have use your example. If a pod is horizontal scalable to assure the application SLA, and somehow you have a quota give to the certain team that you can auto scale up to 10 for your front end jobs, but I have to auto scale to meet my SLA. So how do you solve the conflict between your policies?
So, well, I mean, at one level, we're going to be doing things like preemption. I mean, if you have the ability to evict,
But you can only scale up to 10 according
Right.
to a quota policy.
Right.
But at the same time, somehow you are not meeting your SLA by only
Oh,
scale
right,
up to
okay.
10.
Yes, so that in the end becomes, you're hitting a situation where you need to adjust your policy.
Okay,
Right.
so
We won't automatically change
do
your
you have a
quota.
closed loop that you will tell the user that you need to change the policy because of this?
Yeah, you'd be able to see that your pod wasn't running because it was violating your quotas. So you'd be able to see that. I mean, we could generate, we're using Kubernetes event system for those messages. So you could tie that into, whatever type of analysis system you want to see, now we can throw up an alert if pods are not running because this quota is being hit, we need to change the way that we're doing things. I mean, and that would be obviously, that would be in a situation where, your application is getting hit way harder than you ever expected it to. And you have to do something to kind of, to adjust. You have to adjust your normal policy. And that could be telling your developers they can't, they can't run as many CI jobs right now. We need to take over, 3/4 of the cluster to handle production.
Yeah, so basically what I was describing is just an example of by setting up multiple policy for multiple purpose, somehow at some time you will have conflict between your policies. How do you solve
Yes.
the policy?
Right. So policy conflict is not automatically solved. So this would be something that you would have to observe and adjust.
It's
So-
the user's job to observe.
It would be the operations team is generally responsible for the policy of the system. So they would be the ones responsible for making sure that, what really needed to be done by the cluster is the stuff that was being done, even if input changes. So, hopefully they should be able to develop over time a policy that is fairly static, until they, add a new application, add a new feature or something like that. May require a tweak. But yeah, So it does kind of play into his comment though about simulation. So that would be something where you could be, you could see that this situation was happening, and then you can try out in a simulation making changes to the policy and seeing how the system would have behaved with that type of policy. I think that's the best way to address these types of problems. If you have a very complex, chain of rules and a lot of external dependencies on how the system needs to behave.
Okay, thanks.
Yeah, no problem. Yes?
Is there any kind of check on who can set labels and annotation?
Right, so this is another thing that we're going to be adding, and we're going to be doing that in an emission controller for Kubernetes. So it will be very tightly integrated with Navops command. So we don't want you to have to, configure two things. We actually don't like the way that emission controllers right now are very statically configured. So we're going to reference our API through the emission controller, and that would prevent things like changing. We want to support this concept of an owner that's mutable. So this is an enhancement we want to get into Kubernetes, where you can set a label, and once it's set, it can't be changed. And that's where we want to do something with the owner. So you have some policy that sets the owner when it's created. It could be the identity, that is of the authenticated user at the API server, or it could be something that you allow it just to be set when it goes in. And when it goes in, then it's set, it can't be changed, and then allow, then you attach policy to that in a way that people can't go and manipulate. Because that's a bad thing. If you're trying to make people follow a certain path, and they just, I'm not gonna use that project, I'm gonna use this other project.
And where's the identity coming from? From Navops or from the API server?
So right now this is, we're gonna be using the identity from the API server. there's a lot of work in Kubernetes going on in the API and authentication space, and we don't want to confuse that whole situation. Right now, we have our own little user database. You saw me log in with the admin user. We also have a general user, which is the default user. If we don't put an owner on a pod, it gets this general user, so that you can attach policy to that. But otherwise, we plan on really integrating with that admission control, whatever gets decided there. So the Kubernetes team is very against having like a person owner attached to a pod. They don't like that. And it's because you may have a dev team where, or an ops team where you have 10 people. And yeah, so today, Larry, he created it, but tomorrow Susan's the one responsible for scaling it. So it's not really owned by Larry. It's owned by that team. That's why I kind of brought that up when I talked about ownership. I want it to be, it's more of an abstract construct in Kubernetes land. In our HPC environment, it's the UID of the user who's running the job. But here we want it to be, like I said, it's the person or the group that gets the phone call if that isn't working right. I think that's a great way of looking at it. Anything else?
So this only the policy about do a recommendation. Let's say you have resource, so recommending what on each tier, how many instances should add, equivalent to what. You could do the recommendation for what it increases total scale.
Oh, okay. So that would be, again, that would be something that would be, so you're saying like recommendations on what type of instances to add?
Yeah, which layer, how many instances you should add.
Yeah.
Recommendation.
Yeah, so so that's something that our control product will be able to do. So it would be able to, in the sense that it would be able to look at the work that you ran and the work that wasn't able to run immediately and tell you why. The reason why these pods pended for 4 hours was because you didn't have enough of this certain type of resource. So it can help you identify that, wow, the biggest reason my pods couldn't all run immediately is because I don't have enough big memory instances.
It's not a real issue. Right now it's running fine. But if I have a peak time, now it's just I'm just giving my best guess. But is there more better way to see how to balance each component to scale up in a peak time and then scale down?
Right. Okay. So are you talking about scaling the pods in Kubernetes?
The whole thing.
The whole thing. Yeah.
The
So
whole thing.
this is going into another product that we do have that has a policy engine for dynamically scaling your infrastructure. So that's generally how I've looked at this problem in the past. So it would look at, you can write rules in our policy engine in this other product that looks at what isn't running, analyze what isn't running, and then know how to be able to perform an action if it hits a certain threshold. And then you could have it undo an action if another threshold was hit, doing like simple high water
Typical
blow
media
up.
company will need. Typical media company will need.
Yeah.
I have an
Yes.
event tonight, so I have to pre-schedule that.
Right. Yes.
Give me a good recommendation. What I'm supposed to do? Don't waste my money.
Right. Exactly. So, anybody else? Great. Okay. Thank you.